My name is Rishabh and I'm from CSE AIML branch. Today I'm going to discuss about the shuffling a deck of cards through essential problem solving. This engineering case study examines the problem of shuffling a standard deck of 52 playing cards from an essential problem solving and engineering perspective. It covers problems, definition, mathematical, and probabilistic foundation algorithm strategies, including perfect shuffle, Fisher-Yates, rifle, and overhand models. Object-oriented design for reusable shuffling library, randomness and entropic consideration, secure and performant implementation, testing methodology, instrumentation and extension. The aim is to present a rigorous, extensible and production-ready approach suitable for software engineers, researchers and system designers. Index of content, problem statement, goals and requirements, mathematical background, shuffling algorithm like Fisher-Yales, rifle shuffle, overhand shuffle, perfect shuffle, random cuts and interleaving. Randomness and entropy. Source of randomness PRNG versus CSFPRNG. Seeding and reproducibility. Object-oriented design like API plus UML. Key classes and responsibility. Example Java interfaces and classes. As we move further for the table, implementation details and code is one of the important part of this CEP. Fisher aids implementation, rifle stimulation, secure shuffle using secure random, statistically testing and validation, test uniformity, permutation distribution, chi-square and serial correlation, experimental frameworks. Engineering trade-off, test plan and results, example test cases, security consideration, games, gambling, cryptograph, extension and future work. Conclusion. Problem statement. Design a robust, extensible and verifiable random shuffle system for a standard 52 card deck. The system must support multiple shuffle strategies, be testable for randomness, uniformity, and be suitable for application ranging from casual games to high stakes online card games where fairness and unpredictability are critical. Key question. How do we find a good shuffle? Which algorithm produces a uniform random permutation or a close enough efficiently? How many rifle shuffles approximately randomness? What are the security requirements for the shuffle gambling environment? Goal and requirements. Functional requirements. Provide API to shuffle one or more decks. Support strategies. Fisher aids, stimulated rifle, perfect shuffle, overhand, combined or mixed. Allow seeding for reproduce shuffle for testing. Ability to record shuffle history and undo optional. Mathematical background. A shuffle is permutation of 52 elements. These are 52 factorial possible permutations. A truly uniform shuffle decks each permutation with probability of 1 by 52 factorial. Fisher aids. Modern shuffle. Produce a uniform random permutation if the RNG is uniform over its required ranges. Rifle shuffles can be modeled with Gilbert-Reed's model. The mixing time for the rifle shuffle to reach near uniform is about 7 rifles for 52 cards, a classic result by Bayes and Diaconds. Important matrix: total variation distance from uniform, entropy produced by RNG versus entropy required to sample 52 factorial. Shuffling algorithm. Fisher-Yates model. Algorithm. For I from n-1 down to 1, pick j uniformly from 0 to I. Swap the array of A I and of array A j. Property. The time complexity is uniform if RNG is uniform. Simple to implement. Minimal memory. Rifle shuffle. GSR model. Cut deck according to the binomial distribution. Interleave cards with probability proportional to pile sizes. Multiple rifles approximate randomness of 7 are needed for 52 cards. Use case models human shuffle behavior, useful for stimulation and understanding mixing rates. Overhand shuffle model break off small packets and reassemble in reversed order, slow mixing, non-uniform. Perfect shuffle, in shuffle and out shuffle, deterministic and periodic. Repeated period, out shuffle, return the deck to the original order. Order depends on the deck size. Useful has a theoretical construct and for magic tricks but not random. Fifth, randomness and entropy. Source of randomness. System PRNG example java.util.random fast but not cryptographically secure. CSPRNG for example java.security.secure_random slower suitable for gambling. Hardware like RNG or TRNG highest quality useful for high stakes. Entropy consideration. To uniform sample among 52 factorial permutation requires log 2 52 factorial which is approximately 226.6 bits of entropy. Many PRNGs provide less internal state. Multiply draws can approximate entropy, but cryptographic guarantees matter for fairness. Seeding and reproducibility allow deterministic seeding for test using a user-provided seed. Never reuse seed or expose seed in production randomness for gambling. Object-oriented design API plus UML. Key interfaces and classes. Deck represents a deck holds a list of cards with an operation to cut, draw, shuffle. Card suit, ran to string method, compare to method. Shuffle strategy interface. Void shuffle, deck, random RNG. Concrete strategies. Fisher Ace shuffle, rifle shuffle, overhand shuffle, perfect shuffle, secure Fisher 8 shuffle, shuffle factor, create strategies based on config, shuffle benchmark, utilize to measure time, swaps RNG, call and run statistically tests. Random provider, abstract RNG provider allowing swap between random, secure random or hardware source. Shuffle validator, run statistically tests and provide reports. UML, textual, shuffle strategy of list interface plus shuffle deck, random. Deck. We have to create a list of cards plus cut which is an int plus draw method plus reset method plus size method. Fisher 8 shuffle implements shuffle strategy. Rifle shuffle implements shuffle strategy. Secure Fisher 8 shuffle implements shuffle strategy. Shuffle factory, shuffle benchmark, shuffle validator, random provider. Implementation details and code. Code types. What they represent. Suits and rank are the simple idioms listing the 4 suits and the 13 ranks of the standard 52 cards deck. Card is an immutable value class, final class. Private final suit. Private final rank. That's ideal for a card because it prevents accidental mutation and makes them safe to share. Constructor, getters, equals, and hash code to string should be implemented in usual way. Immutable makes equal and hash code stable. Deck holds the collection of cards, objects and offers operation. Construct a method of build 52 cards in a sorted order. Reset the method to restore sorted state. Shuffle the sorted shuffle strategy S. Random RNG. Cut, draw and size and a get card method which should run an immutable copy or an unmodified view. Fisher aids in place. How it works. Starts at the index of I is equal to n minus 1. Pick an index j uniformly at a random from 0 to I. Swap an element and indices I and j, and these increment I and repeat until I is equal to 1. Secure version. Why do we need a secure version? To ensure the RNG is cryptographically secure so that shuffle cannot be predicted easily. This matters if card is secrecy is a security requirement, for example online gambling. Rifle shuffle simplified stimulation. A rifle shuffle cut the deck into two packs, left and right. Interleave cards from each packet. This implementation repeats this process times times. The intended probability model. The merging step chooses from left with probability proportional to its remaining size of the method left dot size and the method left dot size plus right dot size that approximate a physical plausible interweaving from larger remaining packet contributes more. We have to run a while loop. A while loop runs until both left and right sides are empty. After that, we have to make a probability p is equal to proportion of cards remaining in the left side. Mat.max of method 1, comma right dot size method avoids division by 0. Larger packets has higher chance of contributing next card. Realistic rifle behavior. Randomly pick from the left. Generate a random number from a method random. If it's less than p, take top card from the left. If it doesn't favor any of the condition of the left side, take it from the right side. And after that, merge both of the decks to get the final answer. Statistically testing and validation. Tests to run uniform permutation test ensures each permutation is equally likely, impractical to test exhaustively, so use sampling based test. Chi-square test. Compare observed frequency of sample pattern to expected. Run test serial correlation. Detect patterns across position. Permutation distance test. Measure distribution of card position after shuffle. Example: position distribution test. Shuffle deck m times, record final position of a specific card. For example, ace of spade. Expected uniform over 0 to 51. Use chi-square with degree of freedom 51. Automation. Provide a shuffle validator that runs this test, computes p-values and produce a report. Test plan and example results. Test cases. Unit test. Deck reset, card uniqueness, size, shuffle with seed reproduced expected permutation. Statistical test. Run 1 is 6. Fisher 8. Shuffle with PRNG and evaluate position distribution. Rifle mixing. Run multiple rifles like 1 to 10 and measure total variation distance. Expected observation. Fisher 8s with a good RNG will pass uniformly test for sample permutation. Rifle shuffles approach randomness after around 7 rifles for 52 cards. Conclusion. The engineering solution to shuffling a deck of cards must balance randomness, quality, security, performance, and usability. For most software systems, Fisher aids with a well-chosen RNG is a recommendation default. For human-like behavior or study of mixing times, rifle and overhand models are valuable. For gambling-grade fairness, use CSPRNG hardware RNG with auditing and verifiable protocols. Thank you.